we shall consider one-dimensional harmonic oscillator, 1D harmonic oscillator, and this will be quantum mechanical. Okay. Harmonic oscillator is an important problem also in quantum physics as it is in classical physics, because anything that has a stable structure, if you perturb it, starts oscillating. So quantum objects like molecules, nuclei have also vibrational degrees of freedom. So we shall study this one-dimensional harmonic oscillator starting from its simplest properties. First, we shall estimate the energies and the size of this oscillator using the uncertainty principle. So we shall first, before diving into computations, uncertainty principle. So the energy is the kinetic energy plus the potential energy. That's equal to the energy. And P square over 2m plus 1/2 m omega square x square. This is the energy. This is the kinetic energy. This is the potential energy. And first, let's make it dimensionless. What are the characteristic parameters of this problem? We have m, we have omega, and of course we have h bar. We are doing the quantum. And so to scale the energy, dimension of h is energy and time. Dimension of omega is 1/time. So if you multiply it, that's the energy. So let's write energy in terms of units of E prime, and this is dimensionless energy. We divide by h bar omega, p square over 2m h bar omega plus 1/2 m omega square h bar omega x square is equal to E prime. And if we define P as root m h bar omega p prime and x as root h bar m omega x prime, then the energy equation becomes I am squaring the p, so it is m h bar omega p prime square over m h bar omega 1/2 plus 1/2 m omega h bar times h bar m omega x prime square. That's equal to E prime. So the equation reads P so this is now dimensionless. We like to deal with dimensionless quantities. We got rid of parameters. I'm erasing this part. Now, delta x, delta p, by which I mean delta px, because we are in one dimension, so I will not put anymore x, is like h bar. But we said x was h bar m omega x prime, so it is root h bar m omega delta x prime, and this one was m omega h prime delta p prime. This is like h prime, so let's see, m omega cancels that, root h is h, so they cancels that. So these dimensionless quantities satisfy 1. The uncertainty in x prime and the uncertainty in p prime in these dimensionless quantities is minimum 1, and you can do, of course, worse. Now, I will discuss this equation. If p prime is of order delta p prime, remember this is an estimate. This is a rough estimate. Before we dive into mathematics, we try to estimate it. Delta p prime is 1 over delta x prime. 1 over delta x prime. And if delta x prime is something like x prime, so the energy equation becomes E prime. Now it's a function of x prime. That's equal to 1/2 1 over x prime square plus 1/2 x prime square. So this is the form of the energy using the uncertainty principle. This part starts high for x prime small, gets large as we approach the origin, but then it drops for positive or negative x as 1 over x prime square. This one starts small, in fact from 0, then gets bigger as you increase. So there are two competing trends. So let's say roughly this is something like this. This one is dropping, the other one is increasing. So, and then we are adding this. The question is, where is the minimum? So we will differentiate. dx prime dx prime is equal to 1/2 minus 2 over x prime cubed plus 2x prime, and we will set it to 0 to find the minimum. So x prime to the 4th is equal to 1, x prime 4 is equal to 1, or x prime square is equal to 1, or x prime is equal to plus or minus 1. Therefore, the energy takes the form E prime is equal to E prime of, let me call x prime 0, that solves this equation. E prime of x prime 0 is 1/2 plus 1/2 is equal to 1. Remember, we are solving this in units of h bar omega, so E is like h bar omega. So this gives an estimate that the lowest state of the harmonic oscillator, we expect it not too different from h bar omega. Well, everybody knows its ground state is at 1/2 h bar omega, but this gives a rough, reliable estimate about the size of the energy. Now, what about this x prime equals 1? X prime is x prime square is h bar x is equal to h bar m omega x prime. And x prime square is basically, one should not look at this as the particle is stopping at x prime equals 1, but we should view delta x prime as, or delta x as square root of x square. So it's an estimate of the fluctuation. So this is the way it's fluctuating, fluctuation in position, which is also there's fluctuation in momentum. So if we just draw the graphs, this is roughly speaking 1 over x prime square. This one is x square, and let's say 1/2 x prime square, and they are crossing at x prime equals 1, and so energy here is 1/2. If you take the sum of those, it's not asymmetrical because they are. So this is E prime, this is 1. Remember, this is the dimensionless energy. And x was root h bar m omega x prime, and when x prime is 1, we mean x square average is likely to be h bar m omega. Okay, so this is giving estimate about the size of the lowest state of the oscillator and the energy of the oscillator, which we found as h bar omega. Again, I repeat, these are rough estimates, not exact quantum solutions. We now write the Schrodinger equation for the one-dimensional harmonic oscillator. P operator square over 2m plus 1/2 m omega square psi equals E psi. Again, it's best to make things dimensionless, as we did in the when we discussed the uncertainty principal estimate. So we divide by h bar omega. So E is written in units of h bar omega, and we divide by h bar omega, and P operator square over 2m h bar omega. This one we shall write as by defining P operator as root m omega h prime P prime operator. So this becomes simply P prime operator square over 2. And this one we are dividing by h bar omega 1/2 m omega square h bar omega x operator square. So by defining x operator is root h bar over m omega x prime. So when you square it, this part will cancel that part. So it will have 1/2 x prime operator square. So the Schrodinger equation will assume the form 1/2 P prime operator square plus 1/2 x prime operator square psi will be e prime psi. Everything is dimensionless here. And what about the p prime operator? P operator is h bar over I d by dx. Since it's one-dimensional, we can use this derivative. And this is h over I. X is h bar root omega. So h bar m omega d by dx prime. So this is root m omega h bar 1 over I d by dx prime. P operator. So this is our P operator, P prime operator. P prime operator is 1 over I d by dx prime. Namely, in the x in the coordinate representation. So our differential equation finally becomes one half minus d squared dx prime square psi plus 1/2 x prime square psi, that's equal to e prime psi, or minus now that everything is in the dimensionless form, rather than writing every time prime, 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 sometimes I will forget, x prime, p prime, e prime, we will simply write xpe, but remember that it is dimensionless. So whenever we want to put the dimensions back in, I will explicitly write the form with the dimension. So we get rid of all the primes. So we have psi minus psi double, this is plus x squared psi is equal to 2e psi. So this is the equation we will tackle. But let us pause for a little bit. Again, before diving into mathematics of it, to have the control over the problem, let us think of what we expect. Okay. Well, we want to solve for the wave functions and we want to find the energy eigenvalues. But there is a very simple problem that we can solve, and then we can compare with the harmonic oscillator problem. And the problem of comparison is this. V harmonic oscillator in this case is 1/2 x squared. So it's a potential like this. Okay. There is another problem that one can solve very easily, and it kind of looks like this one, and it is the infinite square well. So here we have an infinite square well. So these branches extend to infinity, and they also get infinitely high, just like this one. What's the difference? This one is very abrupt and vertical. This one has this x squared business behavior. So obviously they are not the same problem, but there are similarities. And Let us consider this problem for a moment. So this problem is simply P operator square over 2m psi is equal to E psi. And P operator square is simply minus h square 2m d square dx square psi equals E psi. If you want to make things dimensionless, there is one length here, natural length, 0 to L. That's the width of this infinite square well. And so let us make this x dimensionless. So x prime goes from 0 to 1 in this case. So let's write it. Minus h bar square over 2m L square d square dx prime square psi is equal to E psi. So here is only energy, and this is also energy. We can check that because h has the units of energy and time. So I have energy square time square, and here m and L square here. So L over T is like velocity. Mass times velocity square is energy. So it leaves energy. So therefore, this is the natural energy unit for this infinite square well potential. So let us write E in terms of this energy, h square over 2m L square E prime. So that minus psi double second derivative is equal to E prime. This is the dimensionless E prime psi, or psi double plus E prime psi is equal to 0. Let's make one more definition to let's say let us define k prime square equal to E prime. So this is psi double plus k prime square psi is equal to 0. So the solutions are immediate. Psi equals a sine k prime x plus b cosine k prime x. Now the wave function has to be 0 at x equal, these are x primes. So psi of x prime equals 0 must be 0, then b is equal to 0. And, well, I don't need that part. Let me erase. Psi x prime L must be equal to 0. That means, x prime equals 1. X equals L means x prime equals 1. So sine k prime is equal to 0. So k prime must be equal to n pi. What is k prime? It is 2 pi over lambda prime. Again, this is the wavelength scaled by the length of the potential. This is equal to n pi. So pi's cancel. So we write it like this. N times lambda prime over 2 is equal to 1. If you wish, you can multiply this by L. N L lambda prime over 2 is equal to L. And this is the actual wavelength of this thing. But let's keep it to that. I am erasing this part. We don't need it anymore. Again, to repeat, we are trying to have some feeling about the solutions to the harmonic oscillator without getting into the mathematics of solving the Schrodinger equation for the harmonic oscillator. And we are just looking at the solutions of the infinite square well, which are very simple functions. And so the ground state by the way, we already got the energy because E prime was K prime square. So we obtain this thing as n square pi square. And the energy is h bar square over 2m L square times n square pi square. So this is the energy of the level n. But I'm interested in the wave functions. It says that, let's look at here, between 0 and 1. So if this is a wavelength, this much is half a wavelength. This is also a half a wavelength. So let us call it a bump, positive or negative. It says that put n bumps into a length of 1. So this is our length 1. So this is n equals 1. So we will just put one bump. This is for the ground state. And the second one, it says for n equals 2, put 2 bumps. This is 2. This is a bump. Put 2 bumps. Okay, one is like this. The other one follows like that. This is the n equals 2. And for the third one and the last one, n equals 3, put 3 bumps. Divide into 3 and put a bump. So these are the wave functions of the infinite square well. Now coming back to the harmonic oscillator, we don't have these sharp walls that make the wave function 0 here. Instead, they should taper off. So I'm erasing this part. Okay, gone. So we expect the harmonic oscillator wave functions, if we can solve it correctly, we expect, so for example, if this is 0, the middle point, we will have a bump, but it will not be a sinusoidal bump, some functions like this, and it should go. So at some place, here is the potential, and the wave function will not be 0, but will die out here. Okay, so corresponding to the second one, we expect, all right, someplace here we are into the potential region, and the third one, okay, they will just taper off, and these are not sinusoidal things. For example, these are just equal magnitude, but these, for example, this bump will not be equal in general to these. So we expect to find something like this. Okay, and energies, at least in the lowest case, should be something like h bar omega. So this is what we are expecting. The question is, will we get that out? Okay. So I am erasing this, and we will start solving this equation. So remember, one bump, but it's tapered off. 2 bumps, tapered off. 3 bumps, it will go like this. And these bumps, this bump will not be equal to those, to that one or that one, etc. But this is what we should get, hopefully, after solving this equation. Or let me write it like this: psi double minus x squared psi plus delta psi is equal to 0. Rather than writing each time 2e, I set delta equal to 2e. Okay? So this is the equation we are trying to solve. I am erasing this part. And everything is dimensionless. Now again, obviously when x becomes very large, this term is dominant. This is a finite number, and so delta is a finite number, so this overwhelms this one. Therefore, it has to be countered by this second derivative. So as x goes to infinity, remember this is our potential, and plus or minus infinity, or x squared goes to infinity. So for a level, if we are way out in the positive or negative x direction, we expect the solution to die. Let's extract that behavior. So psi double is equal to x squared psi. So the solution is psi equals a e to the minus x squared over 2 plus b e to the plus x squared over 2. Of course, this is a solution. Well, they solve the differential equation because the first derivative gives me minus x, the second derivative gives me another minus x, so it gives me x squared, so it's that. Same here. But we must set b equals 0 because otherwise for large x this blows up. So set b equals 0. So that term is gone. So what does this say? It says that as x squared gets very large, x in the positive or negative direction, psi should diminish as e to the minus x squared over 2. So it's we better write now psi as e to the minus x squared over 2 times g, where g is a function of x, g of x. So g will be the interesting function that will determine the behavior of the wave function in the potential region. So we have to do the algebra now. We have to take the derivatives. Psi prime equals e to the minus x squared over 2 g prime minus xg. Psi double equals e to the minus x squared over 2 derivative of inside g double minus g minus xg prime. This was the derivative of that, plus this times the derivative of this. The derivative of this is minus x. So it is minus x times g prime minus xg. So let's collect the terms. E to the minus x squared over 2 g double xg prime minus 2x g prime plus x squared g minus G. What's that? That's the second derivative. Now we will put this into here. All of these psi's have e to the minus x squared over 2. So let me just write and let us notice minus x squared g plus x squared g. So these terms will cancel. That is gone. So for g we get g double minus 2x g prime plus delta minus 1 g equals 0. Let me again call this, let me call this delta 0, let me call this delta 0, and let me call this delta to simplify. I am erasing this. Let's write the equation again. Plus delta G equals 0, delta equals 2e minus 1. So we will solve this equation. So I am erasing this part. Now, the coefficient here 2x and the coefficient here delta, they behave regularly at x equals 0. This goes to 0. This is constant. Therefore, we can expand g as an infinite series, as a power series around x equals 0. So g of x is equal to k from 0 to infinity a k x to the k. So we insert k, second derivative, a k, k, k minus 1, x k minus 2, minus 2, a k, first derivative, k, x, k minus 1, but I have another x, so it is plus 1, plus delta k a k x to the k is equal to 0. Minus 1. Now, this one, for k equals 0, this is 0. For k equals 1, this term is 0. So it's effectively starting from k equals 2. And here all the terms are x to the k. So we can compare the coefficients of the same powers of x. So let me say, since this is a dummy index, let me change this dummy index, k prime, k prime, k prime, because I will define a new index and call it k to compare with this. So k prime minus 2 is k. So k prime is equal to k plus 2. So this becomes k, a k plus 2 instead of a k prime. And k starts from 0. So k plus 2, k plus 1, x to the k. Since the result is 0, let me throw these things over there. That's equal to ak xk 2k minus delta. So we compare the same powers of x. That means ak plus 2 is equal to 2k minus delta over k plus 1, k plus 2 times ak. It is advantageous to write it as follows. Let us say delta is equal to 2 lambda, and this is 2e minus 1. Now our dimensionless energy is lambda plus 1/2. Of course, we don't know what lambda is. Lambda, if you determine lambda, that's the energy. So let me write it in this form. Minus 2 lambda minus k over k plus 1, k plus 2, ak plus 2. I guess I need some space, so I will remember we are doing one-dimensional harmonic oscillator in quantum mechanics. So I'm erasing this part. Let me just copy it up. ak plus 2 is equal to minus 2 lambda minus k over k plus 1, k plus 2, ak. Now, let us see what happened. We obtained we had psi was e to the minus x squared over 2 times g of x. And we had the differential equation for g. And this differential equation was well behaved around the origin. So we expanded g as a Taylor series. And we put it into the equation that defines g. What did we get? We got a two-term recursion relation. So the second order differential equation has two solutions. So we have an even solution with the coefficients starting from a0, a2, a4, etc. and g odd a1, a3, a5, etc. Okay? So let's find few coefficients. Let's consider the g even. We are given somehow the a0 and a2. To get a2, that's k equals 0. That's minus 2 lambda k0, 1 times 2 times a0. And a4, to get a4, k equals 2. So a4 is minus 2 lambda minus 2 divided by 3 and 4 times a2. Let us put a2 into here. Minus minus plus. Two to the square, lambda minus 2 divided by 4 factorial. So g even will go like this. A0 times x to the 0, which is 1. Minus 2 lambda over 2 x square. I can erase this one now. Plus 2 to the square lambda minus 2 x4 over 4 factorial plus etc. It goes, it's an infinite series. Now G odd. We must be given A1. Once you are given A1, A3, A5 are all generated. So A1 is given, then A3, that means K equals 1. A3 is equal to minus 2 lambda minus 1 over 2 times 3 A1. And one more, A5. For A5, K equals 3. That's equal to minus 2 lambda minus 3 over 4 and 5 A3, which is 2 to the square lambda minus 1 lambda minus 3 over 5, 4, 3, 2, 5 factorial. So we can write G odd equals A1 parenthesis x minus 2 lambda minus 1 over 3 times 2 is 3 factorial x cubed plus 2 to the square lambda minus 1 lambda minus 3 x to the 5 over 5 factorial plus, and it's an infinite series. I am erasing this part. Fine. But these are two infinite series. One is an odd function, one is an even function. But do they converge? And or are they normalizable? Because we need to normalize the wave function at the end. So let's look at this, whether even or odd functions. They have these coefficients that satisfy this. Remember, this is just equivalent to the Schrodinger equation in some sense. So as k gets very large, you see for large x, large k values, because it's a power series, for large x, of course, large x terms dominate, and their coefficients are with the large k. So limit k, let's say infinity, I mean large, a k plus 2 over a k goes as 2k over k square goes as 2 over k. Now, how does this look? Consider the power series for e to the x square. So this is equal to k prime equals from 0 to infinity x square to k prime over k prime factorial equals, let's take k prime equal to k at some, So some stage I have x to the 2k over k factorial plus x to k times k plus 1 over k plus 1 factorial plus etc. Because of this form, we can change the index to k prime, let's call it q. And if this is the index, q is always an even number. So q over even. So it is x to k prime is q over q over 2 factorial. So there will be many terms. So corresponding to this one, so let me call it q prime, q prime, q prime. Corresponding to this 2k equals q. So there will be x q over 2 factorial plus x to the q plus 2 over q over 2 plus 1 factorial. Now let us compare these coefficients. The coefficient of this one divided by this one. So it is 1 over q over 2 plus 1 factorial divided by 1 over q over 2 factorial. This goes up, this is at the bottom. And this is q over 2 factorial. This is q over 2 plus 1 times q over 2 factorial. So these cancel. Since q is a large number, we consider a term high up in the series. So ignore the 1. So this goes as 2 over q. So this means both of the series, even series and the odd series, for large x, for very large x, they are behaving like e to the x square. Okay, g odd, g even, g odd, behaving x going to infinity as e to the x square. Of course, this is no rigorous proof in mathematics. This is just an indication that these series are blowing up for large x, but it's not rigorous mathematical proof. But it tells us that we should do something. Both these series, even and odd, are for large x. They are getting very large, infinitely large, and also this is not to be allowed because we found that the asymptotic behavior of psi for large values of x, large absolute values of x, goes as e to the minus x square over 2. So this should be the dominant term determining the asymptotic behavior, not that one. Therefore, we should stop these series becoming like that. Now, what does that mean? That means we have to terminate the series. Well, we cannot terminate, one is lambda minus 0, lambda minus 2. This is lambda minus 1, lambda minus 1, lambda minus 3. So if the higher terms will be lambda minus 2, lambda minus 4. This will be lambda minus 5. The point is that we cannot stop both series at the same time. We stop one, the other one will blow. So for the blowing one, we will set, if it's even, it's A0 equal to 0. If it's odd, it's A1 equal to 0. So we will have one series that has terminated. The other series is totally ignored by setting its starting coefficient 0. Now, I'm erasing this part. That means our g functions must be polynomials because they are not infinite series anymore. They must be terminated at some power. And let's see. So 1, 2, 3, it will go like this, 4, 5, etc. So lambda has to be an integer. Lambda has to be an integer. And positive integer. So if lambda is a positive integer, suppose, let's take the even one. If lambda is equal to 2, x to the 4, the coefficient of x to the 4 is 0. If lambda is equal to 2, the highest power is x to the 2. For example, for the odd series, let's take lambda equals 3, which puts the coefficient of x to the 5 0. The highest term is x to the 3, which is the value of lambda. So one of the series, so let's take a particular example. If lambda is equal to n even, then g even goes as a0 plus a2 x squared, etc., plus a n even x n even. And then we set a1 equals 0, g odd therefore is equal to 0. Because if a1 is 0, a3 is 0, everybody is 0. Or if lambda is n odd, if it's an odd, then g odd is a1x plus a3x cubed plus an odd xn odd, and we set a0 equals 0, g even equals 0. So no matter what, we have one of those, depending on n is even or odd, and we put the starter of the other series to 0. So we have obtained the g. So square g, and we have this power series expansion terminated. And if you terminate a power series, what do we have? We have a polynomial. So g is a polynomial. It's a polynomial of order n. N could be even or odd, a positive integer. Now, they are called, they have a famous name, Hermit Polynomials. They are Hermit Polynomials by some specific choice of the coefficients, which I will describe. Hermit Polynomials. They are Hermit Polynomials if the coefficient of xn is 2 to the n. Okay, so an is chosen to be 2 to the n. So let us determine few simple polynomials. H and x. Okay, so Hn is g such that the an, the coefficient in front of the power x to the n, is 2 to n. So let us begin. For example, h0 x, it is g0, so we will obtain it from g0, which is the even. Okay, g0 is a0 x to the 0, that is 2 to the 0 x to the 0. Well, this is 1. So h0x is 1. Let's take h2 of x. G2x is A0 x to the 0 plus A2 x square. A2 is 2 to the 2, so it is A0 plus 4x square. This is 2 to the 2. All right. Let us look at A2. Lambda is 2. A2 is minus 4 over 2 A0, which is 4, which gives me A0, force cancel, is minus 2. So H2 of x is 4x squared minus 2. So H polynomials are just proportional to G polynomials, such that the power of x to the n is 2 to the n. Let's do it with the H1. So H1 of x is equal to A1 x to the 1. But this is 2 to the 1 times x to the 1. So it is 2x. H1 is equal to 2x. All right, let's do one more. H3x is equal to A1 x plus A3 x cubed, which is A1 x plus, this is 2 to the cube, which is 8 x cubed. And here the coefficient A3 is 8, which is A3. I'm reading off from here. Minus 2. Lambda is 3. 3 minus 1 over 3 times 2, which is 6, times A1. And this is 1, this is 3, this is 2, this is 4. A1 is equal to minus 12. So H3 is 8x cubed minus 12x. So let me write here, H3x is equal to minus 12x plus 8x cubed. All right, so I'm erasing this part. But let us check. We solved the for the wave functions, and what's more, we solved for the energy because lambda was equal to n, so I can erase this part now, right? So our wave function is h psi is proportional to e to the minus x squared over 2 psi n times h n x. So energy was lambda plus 1/2. Now we know En must be an integer, positive integer, even or odd. So it is n plus 1/2. Remember, these are dimensionless quantities. E with dimension, it was in units of h bar omega n plus 1/2. Okay. Now let us check whether we wanted to compare with the square well wave functions. This was one bump, and then there was 2 bumps, and there was 3 bumps with this square well. And what did we expect? We expected them to be sort of taper off rather than abruptly coming to 0. Taper off as e to the minus x square indicates, they will taper off. But what about this structure? Let us see. So psi 0, which is this one, n equals 0, n equals 1, n equals 2. Let's see if we are getting this sort of this structure. Are we getting what we were expecting? Okay. So psi 0 is proportional e to the minus x square over 2 times h 0 of x, but h 0 of x is 1. Therefore, this is just a Gaussian. Okay, this was a sinusoidal bump, half a wavelength. This is not like that, of course, but something similar. So it is bumpy and it is tapering off slowly. So this is for n equals 0. How about n equals 1? Are we getting something like that? So with h1, n equals 1, psi 1 goes as e to the minus x squared over 2 times h1 of x, and this h1 of x is 2x. 2x means it is multiplying this thing on the way up, and because it changes sign, it should go down. It should, for small x, 2x is dominant because x squared is squared. So this is going like this, and then this will take over and will dampen out. And similarly, this will go like this. And okay, here we have it. All right, and one last one. Then we are at h2, 4x squared minus 2. Are we getting something like that? So we have psi 2 is like e to the minus x squared over 2, h2 of x, which is 4x squared minus 2. So it has zeros. 4x squared is equal to 2, 2 and 1. X squared is equal to 1/2. X equals plus or minus 1 over root 2. So here we are. First of all, it has zeros here. And then when x equals 0, it is at minus 2 here. So, and then outside 1 over root 2, this is bigger. It is getting bigger, but then finally it will be tapered off by this exponential. So it will be like that. So it is something like that again. Okay. So it looks reasonable. It seems we solved for the wave function of the harmonic oscillator. Well, not quite, because I'm erasing this part. What did we do? We took the one-dimensional harmonic oscillator. To summarize until now, we estimated the size and the energy by uncertainty principle, which gives a rough estimate. Then we tried to solve the Schrodinger equation for the harmonic oscillator. But before that, we solved a simpler problem of the infinite square well. And this gave us clues on what to expect from our solution. And indeed, we have solved for the wave function. Except that wave functions need to be normalized. And so our wave function psi n x prime is equal to some normalization constant times e to the minus x squared over 2 times hn x. Okay, so this is the wave function, but we have not solved the for the normalization condition constant yet. Now, harmonic oscillator problem physically is physics-wise it's very important, and mathematically it's also interesting. So, in the next lecture we shall study the properties of these harmonic Hermite polynomials in the complex plane. We will find the generating function for these polynomials. This generating function will enable us to compute the normalization constant. From the generating function, we'll be able to find the recurrence relations from in between the Hermite polynomials. And from the recurrence relations, we can again obtain the differential equation. So we started from the differential equation. This is agenda for the next time. Then we will go for the integral representation for the Hermite polynomials. Then we will find the generating function. Then we will find the recursion relations. And from the recursion relations, we will go back to the differential equations. It turns out that all of these things are enough to define the Hermite polynomials. And this technique is a very good example of playing with these special functions of mathematical physics with the example of Hermite polynomials.